to bring this and kind of show it off because this is the end project of the origami talk. They put this together. This is really nice. So we're going to hang it up. We're going to hang it up in the department somewhere. But hopefully I'll have to see it. It's really cool. So what I'm going to talk about today, this will probably be kind of short, very informal. I'm curious, how many of you have heard of zero graphical? Okay, some of you have heard of it. How many of you all know what a ring is? Yes, so I do like commutative ring theory. It's my research field. Some folks refer to me as Sauron. So I'm going to be very informal about it. Structure where you can add and multiply. Now, admittedly, this is extremely fast and loose. I'm going to demand some nice things about the addition, right? That it's a group under addition, that every element has a minus sign. It's got a zero. It's associative. The multiplication is associative and actually distributes across addition nicely. A good sort of example to think of is the ordinary integers, right? Where if you add two integers, you get an integer. If you multiply two integers, you get an integer, and so forth. I will also usually assume commutativity. That is, I will assume that the order of multiplication doesn't matter. Because I'm a lazy man. However, there's interesting things that happen in the real world when multiplication doesn't matter. Any of you that have had a linear algebra class, you've seen that in general you do not expect matrix multiplication to be commutative just because function composition isn't in general. Also, the Rubik's Cube, for example, it has a mathematical structure on it that is not abelian, it's not commutative, and that's why it's so freaking hard to solve, because turning two things this way and then doing it in the other order gives you a different outcome. Now, so I've got this thing, I call it a ring. The multiplication will be commutative. I will always assume it's got an identity, it's got a 1 in it. A good sort of type of example to think about are the ordinary integers. And probably a lot of you in either a beginning math class or maybe a computer science class, I'm going to use this notation to denote the integers modulo n. Although my first number theory teacher would be very angry at me for doing this. So, let me give you guys a concrete example to sort of work with it. And the way in Zmod n that you add things is you add those integers just like they didn't have hats on it. 5 bar equals 5 bar is 10 bar, but then you start wringing your hands a little bit because you don't see a 10 bar within there. But then divide this by 6 and take the remainder and you get 4 bar, right? You can also think of it as kind of a clock. This goes in a circle. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so if you think about sort of adding things up on a clock, that's a good way to think about this. Multiplication works the same way, and there's an effect here in Zmod 6 that you don't have in the ordinary integers. One of the first things that you learn, like when you first take a beginning algebra course and you're trying to set up the, and by beginning I mean in high school, and you're trying to set up the rules for adding or multiplying polynomials and so forth, one of the things that everybody thinks is obvious in these first math classes is when you multiply two numbers, a times b equals 0 means, what does it always say in these elementary books? One of those two animals has to be 0, right? And this is certainly true in the real numbers and things like this. However, if you notice, in this structure here, given the rules that I've talked about, when I multiply 2 bar by 3 bar, I get 0. Notice, both of these elements are non-zero. Their product is the 0 element of the ring. This can actually happen in general. Here's a non-commutative example, and I like to put this one up because it's a little bit disturbing, perhaps. One of the reasons that I do commutative algebra. Is that what I wanted to do? It is. If you multiply these two matrices, and of course I think we can all agree that neither of these two matrices is the 0 matrix, you get 0, 0, 0, 0. However, this will flat anger the blood. You get 0, 2, 0, 0 this way. So multiplying these two non-zero things this way gives you 0. Multiplying it the other direction is not. So you might talk about things like left 0 divisors and right 0 divisors, but that's why I like commutativity. So let me tell you what a 0 divisor is. And my definition might vary from some other definitions that you've seen in the sense that mine is correct. We say an element X and R is a 0 divisor if there exists, if there's a non-zero element of the ring such that X equals 0. Right. So, the way my definition might vary from some other definitions perhaps is if you look at the definition very carefully, you might say in the ordinary integers, X equals 0 is technically a 0 divisor, and that is the way I want it. So, in a certain sense, every non-zero ring has at least 0 as a 0 divisor. However, rings like this are more interesting when they have 0 divisors that are not trivial. If you walk up to a ring on the street, it's probably going to contain some 0 divisors in it. And so, not too long ago, like in the 90s, people started looking at something called a 0 divisor graph, in a certain sense that it sort of measures the interplay, if you will, between the 0 divisor in the ring. So, let me tell you how to build a 0 divisor. Definition. Let R be a ring commutative with identity. Actually, you know what? This is called the 0 divisor graph. Actually, you know what? I take that back. I'm going to go back to gamma because I'm afraid of that notation because I might use it for the 0 divisors themselves. By the way, can anybody tell me what it is? If I'm going to define a graph, what do I need to do? I got to tell you what the vertices are, right? I got to tell you what the points, and then I've got to tell you which ones are connected by an edge, right? So I've got to define the vertex set and the edge set. So I am going to let the vertex set be the set of X and R such that I'm going to take the set of vertices to be all zero divisors that are not zero, right? I don't want, and I'll make clear in a moment why I don't want zero in this set of vertices. Now, the next thing that I've got to decide is how do I decide which pairs of vertices get edges between them, right? Anybody have a logical guess how we might do that? So suppose I take two vertices, X and Y.
The one that you can
Good. That's it. That seems like a logical thing to do, doesn't it? If you want to kind of see how this works. We say there is an edge between X and Y. Oops, Y. If and only if X, Y, Z. Now, given that definition, given that that's my rule as to how to connect two vertices, can somebody explain to me why I probably didn't want zero to be in my vertex set?
because it's connected.
Right, it would connect to everything,
Everything.
right? And I don't really get any good information out of that. Okay, so examples are key to the universe, so let's look at some examples. I'm going to start with this one. I guess I've got to identify my zero divisors first, so I guess I reckon I'll circle in. Let's see, I throw out this because I want the non-zero stuff anyway. Can you identify the zero divisors? That is correct. Because 1 times something equals 0 means that something has to be 0. And 3 is effectively -1. Right? So 2 is in. So let me show you the way that I will do the zero divisor graph. There it is. Kind of boring. Now, one might also, and I'm not going to concern myself really with loops, at least not at this point. One might also do this, connect it to itself, because 2 times 2 is 0. Right? But for right now, I'm going to just leave it like this. So let's look at Z6. Let's see what this animal looks like. Can anybody identify the zero divisors here? Well, once again, I guess I'll throw out 0, right?
2, 3, and 4.
You are correct, sir. So the question is, what set that off for you?
There are zero divisors that, well, there are zero divisors that their GCD is greater than 1.
Okay.
Relatively prime.
Right. So
the GCD with 6. The GCD of that integer in 6 is greater than 1.
I agree.
Right. Not relatively prime.
You guys see what he's getting at, right? You can easily, for these kinds of examples, you can easily pick out the non-trivial zero divisors because they will have a factor in common, a greatest common divisor with, in this case, 6 that is not 0. And here's why it works. Because 2 has a factor in common, right? And I can multiply that by 3 and get 0. 3 has a factor in common, I can multiply that by 2 or 4, and 4 has a factor in common. However, if you look at 5, if you try to solve the equation 5x as a multiple of 6, right? What do you know about k? Let's see, is that right? Yeah, so what do you know about k? Well, 5 and 6 are relatively prime. I guess I could have done this the other way. So 5 must completely divide k, right? Do I agree with that? So k over 5 is in fact an integer. That means that x is a multiple of 6. So if you have 5 times something is 0, that means its x must be a multiple of 6 and is therefore 0 as well. So for this one right here, I have three vertices. And how do I connect them? Well, 2 times 3 I reckon is put them 0. And 3 times 4 is 12, which is 2 sixes, which is 0. However, 2 times 4 is 8, which is 2, which is not 0. So these aren't raised in a V. So that's what this looks like. Let me, here's a couple of more just for fun. Actually, I'll give you a few more. How about this one? Okay, this is another way that you can make a ring, and that is you can take sort of 2 rings and glue them together, right? Consider ordered pairs. And when I add 2 ordered pairs, just like I do in Calc 3, I get another ordered pair, right? But I multiply the ordered pairs point-wise, get another ordered pair. How many elements are in this? How many elements are in Z2? There's 2, so how many are in this ring? Agreed. And that's easy enough for me to write down. And forgive me for not putting little hats on. I'm a lazy man. Now, that guy on top there is the 0 element, so I don't forget about him. Which ones of these are 0 divisors? What happens when you multiply these two? Since it's point-wise multiplication, you get 0. Everybody agree with that? And it's impossible to multiply this. I mean, you can just go through and check it. Right? If you multiply this by something that's 0, you have to have 0 in those slots. Right? So, into 0 divisor. This is a rather dull graph. That's what that looks like. Now, here's one that kind of, I'll give a couple of examples here. Let's see if we can figure out the 0 divisors here. Again, I've got ordered pairs. The first element of my ordered pair comes from Z mod 2, the second one from Z mod 4. How many elements does this ring have? Yeah, it's got 8. And actually, I'll write this down. Well, let's start in order fashion. Okay. Once again, I throw out this guy on general principles. Most of what's left over are 0 divisors. Most of it. Can anybody pick out the ones that are not? One is not a 0 divisor. Right? Because you're multiplying by 1 effectively in both things, so you have to have 0 both sides. So this is actually a unit. In fact, if you can invert it, then it's not a 0 divisor. There's one more. This is effectively 1 negative 1. Also invertible. The rest of these animals are 0 divisors. And this one has a more interesting graphic than what we've seen. Let me draw this one here. So I hope I'm doing it the same order here. before I want to see if we can pick out a pattern. This is like a computer scientist dream. Order triples from Z mod 2Z. There's an easy way to tell if you're a zero divisor here. Can anybody figure out what it is? So you've got 2 times 2 times 2, so you've got 8 elements in here. One of them is the zero element, 0, 0, 0. That's a zero divisor. I'll toss that. There's an easy criteria. If you were like a biologist or something trying to identify something in the wild, you can just look at an order triple and tell that it's a zero divisor. What's that? If it has any zero entry, it's a zero divisor, right? And so, well, let's see, we had 0, 0, 0, which we tossed. The only one that I can think of that has no zero entries is 1, 1, 1. Everybody else has got 1 0 entry. So that leaves me with, it looks like 6 zero divisors. Let me put the typers in first. Yeah. So, I'm going to do these first that have a lot of zeros. These are sort of the reckless abandons. I mean, they're almost zero, right? They've got 2 zero entries. And notice, they certainly don't connect up, agree? Now I've got 3 more, and what the other 3 have in common is they have only 1 zero entry. And I'm going to arrange this like this. Because notice, the only guy that this can kill, you have to have 0 in the last 2 entries, right? So, they'll connect like this. The only one that this can kill has to have 0 on both ends, and this one has to have 0 in the right hand side. So there's some pretty pictures. Now we'll draw a couple more, and I want to see if you guys can pick out a pattern. Or I'm going to ask you a question, perhaps. And of course you can see, do you guys pick up on the pattern that sort of the more copies of this I make, the more complicated it gets, right? That seems to be the theme. Everybody agree with that? So, I mean, this is pretty modest here, right? I mean, what if I had Z2 cross Z10, cross Z6, cross Z2, cross Z2, cross Z2, cross Z200, right? I'm sure that we're just looking at a graph that's a huge mess, right? Let's see what happens when I just take one entry and sort of increase the power. So here's Z4, right? What a yawner, right? How about this? Z8. Well, I'm going to ask for help because I'm going to continue on this way. Can anybody, there's 8 elements, can anybody tell me an easy way where I can pick up an element and look at it until it's a zero divisor? Don't even make me tell you.
If it's relatively prime, it's not zero divisor.
Relatively prime what?
It's in the modulus A.
That's an odd way to put it. But I would say it would be, yes, if it's even, correct? Everybody agree with that? So
Yeah.
if it's even, and that's exactly what you said it was, if it's even, then it'll be a zero divisor. And if it's odd, it's relatively prime to 2, and it'll be not a zero divisor, in fact, a unit. So I've got 0, which I throw out as always. I have 1, 2, 3 zero divisors. Agree? familiar? This looks very much, I mean, as far as graphs go, from just that point of view, looks exactly like the Z6 one we did earlier. Right? But it's certainly more interesting than that first one. Well, let's up the voltage a little bit. Let's go C16. And I've got the same criteria, don't I, for telling zero divisors? They're even. So, how many zero divisors? So I had, what, 3 vertices in this one. How many vertices do you expect I'll have in Z16? How many vertices? 7, that's right. There should be 8 zero divisors. Toss out the one that's 0, and you're left with 7. Well, let me see here. 16, so let's do this. I've got 8, and then I've got 4, 12, and then I've got 2, 6, 10, 14. You guys see the pattern of what I'm trying to do here? That 8 that I'm centrally located because I am singularly bad at drawing graphs. But I put that 8 that's got big fat 3 powers of 2 in it right there in the middle. These two along the top row, what they have in common is they have 2 powers of 2, and these are the little wimps that only have a single power of 2 in them. And notice I can make the observation that the little wimpy ones that only have 1 power of 2, they need to be a zero divisor, they need to pick up the full 4 powers of 2, so they've got to multiply 8 to be 0. This ain't going to be good enough, because you're not going to get enough powers of 2. Now, of course, 4 times 12, that picks up enough powers of 2. And of course, the wings can connect to 8, so can these guys. So, looks like your research area. It's kind of like a squid or something, doesn't it? Now, something bigger. How many vertices, heaven help me, am I going to draw this time? This is the last one I'm going to do like this, right? I do not want to be doing the next one. But I will persevere. Let's see, I've got a big fat 16. I actually think I drew this one up semi-intelligently. Then I've got 8. 16 is 24. So this has got 4 powers of 2. These two animals have 3 powers of 2. And let's go 4, 12, 20, 28. Up there. Let me wrap it in. Right? And then I've got the wimpy ones again. I've got 2, 6, 10, 14, 18, 22, 26, 30. Agreed? Now let's try to connect them, right? The little wimps here only connect to 16 because they need that full 4 powers to blast to 0. Like that. 8's got 3 powers, 24's got 3 powers, so these will certainly connect like this. Notice, any 3 powers, these have got 2 powers, and that's enough. So, all of these connect down here. 4 will connect there and there, 12 there and there, 20 there and there, 28 there and there. And of course, all these should also connect to 16. I'm sure that the graph theorists were drawing it much better than I have. I don't know if it's possible, but that's what that thing looks like. Well, see what happens? Well, I very simple. Here is a theorem. Now let me point out that I've probably just scratched the surface, right? Because A, these were all finite rings, all of them. And B, they were small, right? This was my tour de force right here, and it only has 15 vertices. Let R be commutative of identity, and let gamma of R be at 0 by the graph. Then gamma R is connected. Always. And the diameter is less than or equal to 3. So what that means is pick 2 of those vertices, you can get from one to the other in a path no longer than 3, which I find, especially given the misleading evidence that I gave you here, I find that very surprising. In fact, as far as diameters go, this is as bad as it gets, because this one actually has a diameter of 3. If I want to get from here to here, there is no path shorter than going here, here, here. That's as big as they can get as far as chunkiness goes, right? Any 2 points, you can get from one to the other in 3 steps or less. I think that that is not obvious at all, right? But to me, it's kind of a really cool theorem, because also I can give the proof of this as an exercise in an undergraduate abstract. It's not terribly hard, but this is an example where it's not that the proof is hard, and so we all go fall at your feet for proving this because so to Riemann hypothesis or something. It's actually fairly easy to prove. It's just a very interesting observation, I think, that you wouldn't have guessed at.